Welcome back to trigonometry. In this video we're going to talk about modifying the basic trig functions into kind of more general ones. And the idea here is that in the real world there are all sorts of periodic phenomena, things that repeat over time or over other quantities that are really well modeled by trigonometric functions, especially sine and cosine. The problem is just plain old f of t equals sine t is not really strong enough, right? If you want to work in, your own units, meters per second or hours or amperes or whatever, you're going to need to stretch or shift your sine and cosine function to fit whatever situation you're modeling. So just sine t won't really cut it. We need to kind of tweak it a little bit to make it more general so it can fit lots and lots of different real-world situations. Okay, so what we're going to look at is a function like this. Our goal is going to be to look at this function, f of t equals a times sine of, and all of this goes into the sine, the bt plus c. So remember that t is the variable here, and then we think of a, b, and c as fixed constants. So you might have something like f of t equals like 4 times the sine of 3t minus 1. Something like that. So this would be a equals 4, b equals 3, c equals negative 1. Okay? And what we want to do is figure out how those sorts of functions work, and essentially, since we know how sine works, we want to compare how a sine of bt plus c compares to just sine t. Okay, so we'll take these letters one at a time. Let's start with a, because, well, it's the first letter in the alphabet. So let's look at a little example. Let's look at, say, a equals 2. So we're looking f of t equals 2 times the sine of t. Keeping it pretty simple. And let's just plot a couple points. So what about f of 0? Well, that's going to be 2 times the sine of 0. That is still 0. Great. What about f of pi over 2? Well, that's going to be 2 times the sine of pi over 2, but we know the sine of pi over 2 is 1, so it's 2 times 1, which is 2. Note that I'm plugging the value pi over 2 into sine before I multiply by 2. So you resolve all the sine stuff first, then you multiply by 2. F of pi is going to be 0 again, because it's 2 times 0. And f of 3 pi over 2 will be 2 times the sine of 3 pi over 2, which is negative 1 times 2 is negative 2. And you can kind of maybe now imagine what the graph is going to look like. If we have pi and 2 pi here, then instead of going up to a maximum of 1 and going down to a minimum of minus 1, the same thing, sine in the sine of, 2 sine t is going to look the same in overall shape, but it's going to go up to positive 2 at pi over 2 here, instead of just going up to positive 1. And at 3 pi over 2, it's going to go down to minus 2. So it's going to be much higher. Then go back down and go down and back up. Okay, so what we're seeing is that this is stretching it vertically. This is stretching it vertically. So we give a name. This is called the amplitude. In fact, if a is negative, we still like to have the amplitude be a positive number, so we take the absolute value of a. And this is called the amplitude of f of t. So you can talk about the amplitude of sine t or cosine t. With tangent, it doesn't make as much sense, but I guess you could do it. But that's what we're looking at. Okay? So let's graph a couple of these. Oh, you could probably imagine if I had f of t equals like 3 sine t, it would do the same thing, except then everything would get multiplied by 3. So instead of going it to 1, it would go all the way up to 1 times 3, and so on. So let's look at the graphs of a couple of these. Here's our first regular old sine t. Goes up to 1, goes down to negative 1. Say I want to graph 2 sine t on the same graph, well, then that's going to go up to 2 and down to minus 2, but I'm not changing the period, I'm not changing where it's 0 or anything. So it's going to look something like this. Oops, that's supposed to go back to the same place, but you get the idea. And what if I want to graph 3 sine t? Again, I'm not changing the 0, so it's still 0 at 0, pi, and 2 pi. But now the max is going to be at 3, and the min is going to be at negative 3. So it's going to be even taller, something like that. And you can actually do this with negative numbers as well. I'm running out of colors here. Let me use gray. So what if I want to do y equals like -1 times the sine of t? That's actually going to flip the graph upside down. So then it goes down to -1 and up to +1, and it's going to look something like that. And you can imagine -2 sine t, -3 sine t are just going to look like 2 and 3, but flipped. Okay, so that's the amplitude. It's a vertical stretching. One thing to notice is that the amplitude in a graph is the distance from the middle to the top. So this distance is 1, right? That's the amplitude. And this distance is 1. And in like 3 sine t, this distance is 3. That's the amplitude. So it's always the distance from the middle to the max or from the middle to the min. Okay? Okay, so amplitude. Great. We know how to stretch things to be bigger or smaller in the vertical direction. So what next? Well, what about this constant b? So now we're looking at things like f of t equals the sine of 2t. This would be b equals 2. So what's this going to do? Well, again, let's try plugging in some points. So if, let's say, t equals 0, we're still going to get sine of 2 times 0. That's still going to be 0. No trouble there. How about pi over 4? Well, now this is going to be the sine of 2 times pi over 4, which is pi over 2. And the sine of pi over 2 is 1. Okay, before we had to go all the way out to t equals pi over 2 to get 1, but now we only have to go to pi over 4. F of pi over 2 is going to be the sine of 2 times pi over 2. That is the sine of pi, because the 2's cancel. Sine of pi is 0 again. And f of 3 pi over 4 is going to be the sine of 2 times 3 pi over 4. So we do some cancellation, and we get 3 pi over 2, which is -1. And then if we go back to 2 pi, or excuse me, just pi, we get to pi. That's going to be the sine of 2 times pi, which is 0 again. Okay? So what we're seeing is, if we graph this, that we only have to go out to pi before the graph goes all the way up and all the way down. That was pi over 4 and 3 pi over 4. Oh, that's a bad graph. So it goes all the way up and back down and does a full period in half the time. And you can probably imagine, if I were to put in larger values, it would just repeat again. So if I go all the way out to 2 pi, and this is going to repeat again, and it does 2 full periods just in the original interval of 0 to 2 pi. So you can kind of see what's going on here. If we look at sine of bt, then the period is going to be 2 pi divided by b, because it repeats itself that many times in the interval from 0 to 2 pi. Okay, so here we're changing the period. What we're really doing is compressing it or stretching it in the x direction. So multiplying on the outside, out here, like a sine of bt, that would stretch it in the vertical direction. Multiplying on the inside stretches or compresses in the horizontal direction. Okay, and that's going to change the period. Okay, so let's look at the graph of this. Say we have our original sine t. What if we want to do like sine of 2t on this same graph? Now this is going to go same amplitude, so we're not changing the amplitude. So it's still going to go up to 1 and -1, but now it only has to go to pi over 4 to get up to 1, and then it goes back down to 0 at pi over 2, and then it only has to go to 3 pi over 4, so it's going to do a full wave in half the time that the original function took, and then it's going to do the same thing again and just keep repeating. Okay, and you can probably imagine what would happen if I were to graph y equals sine of 3t. It would be really, really oscillatory. It would go up and down very, very fast, so it gets kind of hard to draw. We'll just leave that to your imagination or your calculator. Okay, so what about c? What if I want to look at f of t plus c? Well, you've actually already done this in pre-calculus, or maybe even before that, when you look at shifting graphs in general. If you have any function and you look at f of t plus c, that's going to be the original graph shifted to the left, assuming c is positive. If c is negative, then it'll shift to the right. And that's basically what happens with sine of t plus c. If we look at y equals sine t, there's our sine t graph. Now what if I want to look at sine of t plus c? What that's going to do, let's assume for the moment that c is positive. Well, instead of being 0 here, it's going to be 0 back here at negative c, because I'm shifting to the left by c units. Okay, so this is not actually a 0 here. So it's going to look exactly the same. The amplitude isn't changing, the period isn't changing. What it's doing instead is it's going up and down, shifted. Okay, the maximum doesn't have to be at 0, that's just how I happen to draw it. But each point on the graph gets shifted c units to the left. Assuming again c is positive, you would shift it to the right if c was negative. Okay, so that's not too bad, and you've done that sort of thing before. The interesting thing comes in when we look at something like a combination of sine of 2t plus 7. Changing the amplitude doesn't really mess with anything, they don't work together, but both of the 2 and the 7 are inside the sine, so we have to be a little bit careful with that. So the way to think about this is that you're shifting it left or right, and you're compressing it. And the real question is, you have to think about, like, are you compressing first or are you shifting first? Because it's going to make a difference. So the way to think about this is to rewrite it. I'm going to write this as the sine of, I'm going to factor out a 2, and then I have t plus 7 halves. Okay? If you don't believe that's how it factors, just multiply the 2 back in on both parts, and you'll get the original function back, 2t plus 7. Okay, so what we see is that we need to actually shift by 7 halves, and then we have a period of 2 pi over 2. So we're still dividing the period in half because of the 2 here, but we're not shifted by 7 units anymore, we're shifted by 7 halves. Okay, so well, it's going to be messy if I try to draw it, but you can just imagine we're shifting by 7 halves. So in general, f of t equals sine of bt plus c has period 2 pi over b, just like before, and is shifted by negative c over b. Okay, so that's left by c over b if c is positive, and right if it's negative. And that's really the interesting part of this. Okay, so there is a name for this shift when we're talking about sines and cosines, because we're dealing with waves. This is called a phase shift. Okay, so we say that this has a phase shift of negative c over b. So up here, this function has a phase shift of negative 7 halves. Okay, so let's just recap this. There's a lot there. So we have our function, a sine of bt plus c. You really need a and b not to be 0 in order for this to make any sense. Otherwise, it's not really an interesting function. So what does a tell you? A tells you the amplitude. So that's either how high you go up to get to the max or down to the min. Or you can think of it, this is how I think of it, it's the distance between the middle and the peak, or the middle and the peak on the bottom. Okay, what about b? B is telling you the period, and that's really the distance between the, well, you might call it the wavelength, but it's the difference between the peaks or the difference between alternating zeros. So you can think it's the distance from like this point to this point. Okay, so from here to here. So that's the period. How long does it take to repeat? That's what b changes, because it's compressing it or stretching it in the x direction. And then that c is going to give you a phase shift combined with b. So if there's no c, then b doesn't really phase shift at all. But if there is a c, then you have to take the b into account. And that's how far the graph shifts to the left or the right. And you can always find that. You can figure out what it is by looking at where the graph is 0. So if I look at this 0 right here, that's going to be at negative c over b. Okay, so that's a lot of stuff. And with these more general functions, we can model all sorts of real-world physical situations. And that's what we'll talk about next time. I'll see you in class.